And it's given by a new number, another constant, which is given by minus chi phi. So again, it looks similar, and it is similar, but we will now simplify a little bit the problem. So there is a second coefficient, k of phi. This has no units. Now, this equation, in principle, you have also trigonometric and cosh or hyperbolic functions, right? But we will simplify this, and we will assume that the geometry is closed. What do I mean by this closed? There is the following. Let's go to these examples. If I do a rotation here in the phi direction, let us assume that the solution comes back to the same solution, right? What does this mean? Can we have cos and sinh, or cos and sin? We can have only cos and sine. So here we will take only cos and sine. So this is only cos solutions and sine solutions. Soon we'll write them down explicitly. Again, cosine k phi, take the second derivative, it's easy to show that this is a solution. There are exceptions for this. When do we need here? In principle, we will not do that. When do we need also sometimes the cosh?
When we don't have a full rotation.
When we do not have full rotation, and we had a similar problem when we looked previous class, when we looked at this cone. Because if I had instead, in principle, let's say I'm taking a slice of cheese out of the very bad type of doing something like this. So you see, I took out a slice out of this cylinder. In this case, there's no reason why the solution here, when I go back to 2 pi, will be the same, because in the middle there is nothing. And in this case, you will need the cosh and the shunts. But okay, let's look at this. Something simple that I can do a rotation and come back to the same angle with 1 2 pi thing, just to simplify things. We can make things complicated if we want, but we don't want to do that. So here we'll have also the cosh and sin solutions, not under consideration. So obviously the main equation is what we get from the r direction. That is, now I go out here like that, right? And this equation, I think you know it. What is the name of this equation? The Bessel equation. This will be the Bessel equation. And the Bessel equation, again, it comes from the Laplacian. I'm skipping all the details. Is this equation, d over dr. It's the radial equation, d capital R dr. Here I have an r inside. Plus kz, which is a number, squared r squared. So remember, this is dimensionless, and this is also dimensionless, so I played a little bit with this equation. Minus chi phi squared times r equals 0. So this is the main equation that will cause some headaches, because these equations are very simple equations. It's not that this one is so complicated, but it presents Bessel functions. Now, are you afraid of Bessel functions? Don't lie. It's a bit intimidating. So how many Bessel functions do we have? In general? No. 2.
Yeah.
4. There are 4 Bessel functions. Is the number 4 surprising? It's not so surprising. It's like the cosh, sinh, cos, sin. So some of them will be oscillating and some will be decaying. But the fact that you have 4, and 4 is bigger than 1 and even bigger than 2, makes it, in my opinion at least, a complicated problem, because you have 4 functions to choose out of. You are used to choosing between these functions, more or less, decaying solutions and oscillating solutions with a quotient. But now you need to be familiar with these functions, the four Bessel functions, in order to try and solve this. And this is a mess. So we have four Bessel functions, and we have in principle, four functions here, and we have four functions here in principle. So there are different types of solutions. We need to understand, what are these solutions now? Of course, you cannot remember all these Bessel functions, the j, the I, the y, the k, but you need to kind of know a little bit about them in order to forget about it, and then later on, when you want to look at it again, you'll look at it and know what to look at. Okay, so that is the goal here. You don't need to remember properties of Bessel functions. I don't want to pretend that is correct. So we'll come back to this Bessel function soon. So the easiest thing to do, first of all, before advancing, we're going to solve the trivial equation for phi and identify what is k phi. And this comes from the periodicity. So since phi, the function phi is equal phi plus 2 pi, then we can choose the solutions as what I call trigonometric solutions, and I can present them, for example, as phi as exponential minus or plus IL phi, and L is an integer. So it's a kind of quantization, but it's a trivial quantization. It's simply because of this condition that you want to, if phi is 0 and phi is 2 pi, it's the same thing, right? So here comes the fact that L is some integer. Okay? And we solve this equation, and this, what is this L? What is the L squared? This is essentially this chi phi here, right? Because you take the second derivative, this one is chi phi, right? So now you know what's chi phi. I didn't need to work hard to get it. Then we will do the following. This equation has kz inside of it, so we want to massage it a little bit. So let us define x as kz absolute value. I mentioned before that kz can be in principle imaginary, so absolute value, just its value, times r. So x, this is a dimensionless variable. It's just a position r going out, if I'm the cylinder going out like that, right? So plugging this in here, I'm not going to do the math. I'm getting, you see here I have r d over dr, r d over dr, so obviously all the k z will cancel out here. I'll get this equation d over dx, x dr over dx. So all of what I'm doing here is very simple. I'm writing the equation in dimensionless form, getting rid of one variable, this kz, by plugging it into x. And then I have plus or minus L squared. Okay, the second thing is I identify this k phi with L. So I have this thing here, r equals 0. And the plus sign, here you have a plus or minus. Plus sign is when kz squared is positive. And this is the Bessel equation, just written in a slightly different form than what we have. Okay, so now I mentioned there are four solutions of these type of equations. Two of them related to the plus, two of them related to the minus. And now Nadav Schneeb suggests, let us write the solutions in a kind of table. And if you have this table and you know how to read it, then you can solve many different problems. It's a very practical idea, that's all. So his table is the following. And we will use this table to solve problems. And by the way, if you look at this book, you will find similar tables for other coordinate systems. It's not, this table is not really unique to the cylindrical one. And in essence, when you solve these type of problems, you use something like this table, but you didn't define it as a table. I think he's just organizing the material in a very nice way. So let us write the table, which is useful. And in this table, we have three functions, right? Capital R, we have capital Z, and we have this phi. And I'm summarizing. So this is going to be option 1, I'll call it Aleph, some Hebrew. And that is when kz squared. Again, I still didn't say how do you determine if kz squared is bigger than 0 or smaller. This will come from, again, from the boundary conditions. We now assume that kz squared is bigger than 0, then this is some a, ya, because that's the first letter in the alphabet. So a is some constant. It's to be determined later by boundary conditions. K. What is K? Okay. K is Kz absolute value. Just the number. So sometimes it can be positive, sometimes it can be negative. This comes here. This is this K. I just write it in a shorthand notation, only with K. It's positive. Okay, so that is JL. And okay, soon we'll have to explain what this mess means. B, YL, KL. What is J and what is Y? These are some Bessel functions that exist on ChatGPT and they exist, people know about them. Okay? If you want to think of them now, these are like cosines and sine. Instead of these two functions, we have J and Y. And they solve this equation. And soon we need to discuss what does this mean. In this case, we have C, another constant, sinh kz, plus d cos kz. This I already mentioned. This was on the board. I'm just now repeating what was before. I mentioned before that if this kz is bigger, then the solutions in the z directions are these exponentially decaying or exponentially exploding functions, and that's why I have the sinh and the cos here. Yeah.
And then it's supposed to be kr and not kl in the yl.
No, this is a function of r. This is a function of z.
No. In yl
It means that YL.
plus
Yeah. This
okay.
is r, of course. Thank you. Thank you. I make mistakes deliberately so you can find them. No, not really. I make mistakes. Thank you. And then, what do I have here? Here we said we have the simplification. Here we only have the oscillating solutions. So this is because of the geometry we assume, and also because I don't like to write so many things. So this is cosine phi. No, the E will be with a sine. Plus B, no, after E. F cosine phi. So what will be the solution here, down here? This is of course Kz, let's call it B, Kz less than 0. So what is the solution here? I said it already? What?
Same thing.
Same thing, because I mentioned, that's why I like to write it, so this means the same as this. Here it's easy, because of the rotation of phi, as before, this was mentioned.
Where does L fit into the phi equation?
Oh, you're absolutely right. I guess I'm very... This is L, thank you. L. So this is because of the rotation of the 2 pi, which was mentioned already. What will I have here? I think you see already. You'll get these, instead of shins and cos, you get some sinh. You get here the following. C sine kz plus d cos kz. And what will I have here? Here I'll have an A, and I'll have a B. So the solutions are either these or these. At least in the problems we solved, they're either these or these. And here I have 2 more Bessel functions, which are denoted as IL KR plus BKL KR. Okay.
The K's are KZs.
The K's are given here, absolute value of KZ. So this is the framework, which is a very general framework, but it's also still in some sense not useful, because how do I choose this one, that one, this one, that one, etc.? There are many combinations. And I mentioned already, these combinations are determined by boundary conditions, and the idea here is, let us use this table in order to solve all kinds of problems. You have this table in front of you, and it helps you navigate in this kind of maze of solutions, okay? That's the goal. So let us see how this is done. But to do that, what do I need? I need to know a little bit about these functions. Without knowing something about these functions, you cannot choose these functions. That's very trivial. So what do? You go to the internet and you look, what are these functions? Or some properties. This is not a course on Bessel functions. Some properties of Bessel functions. What is the most famous Bessel function? Or mostly used in physics, I'll put it this way. In my opinion, at least. The J. So let us look at the J. Well, it also comes with the A here. So the Bessel function, what do you need to know a little bit? It's a function now of x. So I would like you to remember more or less the J0. Why is 0 important in many problems? Not all problems.
Because in 0 it's not it's 1, not 0.
That is also true in some cases, but I intended you to answer different. Why physically L equals 0? When L equals 0 will be important?
There is no dependent on the
azimuthal angle. So let us look at this type of problem. For example, this is V, the rest is 0. The solution is rotationally invariant. The phi here, or the phi there, or the phi there, everything is the same, right? Which means there's no phi dependence in this solution because of the symmetry of this type of problem. And then what? If there's no phi, what does it mean? L equals 0. So it will help you choose L equals 0. So in other words, you choose L equals 0 here because of the symmetry, but it influences these solutions by a selection rule. Now, you can break the symmetry in phi. For example, if the potential along this thing depends on phi, then this will not be true, and you'll have to have all the L's. It's not that L is always 0, it's sometimes 0. And this is why J0 is very useful in many problems. We like it. And J0, as was mentioned here, also has a mathematical property different than the other ones, which is also worthwhile measuring. It looks something like this. It starts here from 1. While the other Bessel functions, I'll soon plot them, do not start from 1, they start from 0. And this is important because, why is this important? Because sometimes the boundary condition is what we identify here, x equals 0, and the solution is not 0 there. And then you will many times want to know this, that the solution is not 0 there, it goes to some constant. This is very useful. So in this Bessel function, there is another thing that you need to know, or not the details, and that is the z. The z's are, it's very annoying, but it's not this z. It's a different z. This z is from the what? Zeros. So these are the zeros of the Bessel function, which I'll denote like this. z0, 1. So there is indexes. These zeros are going to be important. What are these zeros? What is 0? This index 0 is actually in general L. And what is this index 1? This is the first 0. So here what do I have? This is another 0. That will be 0 of the Bessel function of L equals 0, 2. So I have all kinds of zeros on the x-axis. The first one is something like 2.4. This is like 2.4. They are not evenly separated. They are a mess. But we have good friends and the mathematicians, and they found them, and they are all tabulated, and we know them in principle, in books, so we know them. And these zeros will become important where? Can anyone guess? What trick will they be very important in? We'll soon show it, but it is important when we define what?
Zero boundary conditions?
Not also that, yes, you are correct. But another thing would be the orthogonality relations. They are related to these zeros. I'll explain that too, but you are also correct. So how does the other j's look like? So the other j's start like this. For example, j1, all of them, they start at 0. This will be j2. They all oscillate, etc. They go to 0 at large distances. They don't explode or don't diverge, but they do this in an oscillatory function. Okay, these are the j's. It's a crash course on the j's. So what is the orthogonality relations? And this is something that later when you use these orthogonality relations, you know these orthogonality relations by when you expand in a basis. In quantum mechanics, there are many different similar things to find solutions. But actually, when we solve the Laplace equation, it's hard to know which orthogonality relation to use, because sometimes it will be an orthogonality relation of the signs, sometimes of the Bessels, and you need to know which orthogonality relation to use. So there are many, actually. They are not one. Okay, there are many functions here, so there are different types. But one orthogonality relation is this equation, which I'm not proving, but it's a useful equation. A squared integral from 0 to a r g l zn l r over a j l. So notice here I hope I don't make mistakes, because here you cannot I think they don't, you cannot check. Okay, you can check it by look at ChatGPT or something. So here L and L, this is not a mistake. So these are the same numbers. Usually when you have, let's say, orthogonality relation, let's say between sine and another sine, you have two different indexes, right? What are the indexes actually? They are going to be the zeros of the Bessel function. So here I have Zm of L, the same L all the time, R over A, dr. The magic is that this is JL plus 1. So this is like the normalization constant. Z M, doesn't matter if it's M or non L, L squared delta MN. So this orthogonality relation, soon we can use it, or maybe we'll not use it depending on the problem. You see, here I'm having the nth zero, and here I have the mth zero of the lth Bessel function. If the n and the m, that is, I'm using two different zeros, then these equations are orthogonal, but if they are the same, they give you some number. And it's a Bessel function of L plus 1 of the zeros of the L's function. So it's not a trivial equation. I'm not claiming it is. It's taken from some book. And if you want to have some analogy, think about, let's say, what is A? For example, A will be some length scale like the radius of the physical meaning of A will come later. But you can think about it a little bit, let's say, when you have this Fourier series, and you have a sine km of x, and then you want to have orthogonality. So the orthogonality comes from the km, which are this prefactor in the sine functions, and now they come from the zeros of the Bessel function. It's not the same thing, but it's a little bit similar. This analogy, at least for me, it's useful. So this is one type of orthogonality relation that you also need to have in your toolbox. Okay, so now this was a brief introduction to J's, and now you need to know a little bit about the Y's. The Y's. The Y's, IL. No, I'm going to be, now I want to say the Y's. The Y's come together with the J's. Here, at least in the table. And their main property, or some of their main property, so this is a function of this x. They diverge. This is important. They diverge at the origin. This is one of the reasons where, I'm not saying that you never use y, but they are less popular than the j's that are well behaved here at the origin. This divergence is important for you to remember simply because in many physical situations you can say, oh, the physical solution does not diverge, and then I can throw these y's to the trash can, and then this b will be 0. So you need to just know this. And these solutions are kind of oscillating. So and then I1 will be the same one, etc. So they diverge on the origin to minus infinity. As a side remark, they also satisfy this type of orthogonality relation. So you just replace j with I. You see the zeros here of different values, again in textbooks. And
do these functions have the same zeros?
No, not the same.
So in this orthogonality relation, when we replace j with y, we also replace the zeros of j with
yeah. Sure.
Yeah.
They're not the same. Okay, what are the other functions? I don't want to kill my nice thing. So we have j, we have y, and now we have I. And how does I look like? So you see these solutions are oscillating with some complicated structure. What are the next two solutions? They are just decaying, kind of more boring, like the exponential is more boring than the cosine. If you like hills and valleys, that's what I mean. So the I looks like this, IL. There is again a difference between L equals 0. This is the L equals 0 branch. And this is the L not equal 0. So this is L not equal 0. What I mean by this, not all the L equal, not L1 and 2 and 3 look differently, but all of them go to 0 x equals 0 when L is not equal 0. It goes like x to the power L. There is a prefactor here, which is a gamma function. We don't care about it. It goes to 0, and you see when L is equal 0, this goes to a constant. I think this constant is 1. Okay? So these are important things to remember. These are not oscillating. And they diverge when x goes to plus infinity. They diverge exponentially. This is also, they diverge exponentially, like some very strongly they diverge. And then the last part I want to have is after the I, then I have the K. And you see here one solution diverged at the origin, the other one didn't, and here the same thing. This solution compared to this one now, this solution looks something like that. It decays to 0, unlike these ones that go up to infinity. This decays to 0 exponentially, like e to the minus x times some polynomial, and they diverge here. This is for every L, but there is no solution. Like these y's, all of them diverge and oscillated. Here, all of them diverge and do not oscillate. So these are the general picture of these things. Now you need to have this in mind, more or less. And now we need to, if you have this picture, then you can, more or less, I think, kind of choose these functions based on boundary condition. And that's the trick, and this is what I want to do now, okay? So what I'm trying to do now is clear? Okay, so for that we need to do boundary conditions, and to do boundary conditions we want to use some specific examples. And what I'll do is I'm going to present the solution, and then I will think about this solution, and then I will say, okay, it's this solution or that solution, and then we will choose these coefficients. That's the goal. Okay, so a relatively simple problem, which I think you also had in your class, in your homework. It's a bit of a problem that I have to delete. Maybe I'll delete this one. Soon I'll delete everything, but I want to leave the table. So it is a cylinder of radius A with 0 potential on the tops, I mean tops and bottom, and V on the side. In other words, I have the radius A, and this is my cylinder. This is also A. On the top, here, potential is 0, and here potential is 0. So do you understand? This is like a Coca-Cola can. On top the potential is 0, on the bottom it's 0, and around it is some V, some constant V. This here, this length is 2a, and this height is going to be denoted by h. Some height. This cylinder has some height. The cylinder has a radius. And this is a definition of the problem. Of course, what I mean by definition of the problem, I'm looking at the solution of the Laplace equation. So, what will we say now? So the first question you need to ask yourself when you look at this table, what is the easiest part? Let's start with the easiest. It's always a good idea. So, okay, but here there are two easy things. Maybe I'll delete this. what do I mean by start with the easy? In my opinion, the easy, maybe you don't think so. So the easiest part is this one and this one. These two guys are the easiest ones. So let us start. I'll start with this one. Why do I start here? Because this one will help me determine this one or this one. Am I on this line or am I on that line? Well, this one and this one are the same, so it doesn't really help me to determine if I'm here or here, because these guys are the same. So let's look at this part of the table. And what is the solution in this problem? What?
The sine and cosine.
The solution should be the sine and the cosine. Why? Because of the boundary condition on the top and the bottom is 0. Ah, that's good. So it's the sine and the cosine, which is actually trivial, but here it gives you something more. If this is the solution and this is the table, it means it's not j and it's not y, it's maybe I and maybe k. So we are now on this line. Okay? So the first noticed is the potential is 0 on the tops. So cosh of z is going to go away, sinh of z is going away, solutions are is cos z. I'm not writing everything and sine z. What does this mean? As I mentioned, this means we are solution of type B. Bet. That is kz squared is less than 0. We selected one of them. What is also easy to say here in this table?
A is equal to 0.
L is equal to 0. It's easy because I even said it before. So L is equal to 0 is also very easy. Why? Again, I mentioned this because there is a symmetry here. If I go to this phi angle or that phi angle, all of them are the same because it's a very simple problem. So L is equal to 0. Okay. What else?
A is equal to 0. No, actually B. B is equal to 0.
B is equal to 0. Okay, so now we look at this table and then we can say, okay, B is equal to 0. Why is B equal to 0? Because this solution diverges, as I just mentioned before, it diverges when R is equal to 0, which is exactly in the middle here. What else can we say? B is equal to 0, so here there's only one solution, I0. B is equal to 0. Good. What about these guys? You have C and D.
You take only G equals to 0.
Well, it depends on the origin.
The origin,
Doesn't.
this is 0, this is H. You're right. So, as you said, what did you say? But you're right. Don't say it again because you might be wrong. But what did you say? D is equal. You said D is equal to 0. Why did he say that? This is correct. After correcting me, defining the reference frame, because the sine at 0 and up here can be 0, but the cosine at 0 at least will not be 0. And what else? If sine kh is 0, now what do we know? We know k. Okay. We know k because this is the quantization of k. Up to now we didn't know what k, I just gave you something general. So d is equal to 0, and also we know sine kh is equal to 0. So what is k? The absolute value. It was called kz before, or k, doesn't matter. This is simply given by n pi over h. everyone can see that if I plug here n pi over h, and n is an integer, can n be 0?
No.
No. Why? Because sine of 0 is actually 0 and there's no solution. So it starts with 1. So this is n equal 1, 2, 3. So this simple example, maybe you disagree with me, it's okay. Maybe you can tell me this is a simple problem, but at least for me, this table, once I had it in front of my eyes, this solution was rather easy. Did it help you? Is it helpful or not?
Yeah.
You can say yes, you can say no. Okay, so this type of organization, and again, this is not limited to the Bessel one. It's very easy. Now we can just summarize this and write down the solution. Now remember, the solution is not r times z times phi, it's an infinite sum. And the infinite sum comes as usual from this kz, because I can sum over different n's. I'll have an infinite series, of course. So I didn't solve the problem yet. But up till now, what did I find? I found the solution like this. I found a solution which is in cylindrical coordinates. It's a function of r, phi, and z, and it's given by an infinite sum. I don't know why I called it an. It's not related to this a. Maybe I should have called it c, but I want to call it an. Okay, sorry about this. This is like the c here. Sum constant, and I know how to sum n equal 1 till infinity. I0, y0 again, because of the phi symmetry, L equals 0. Here I have n pi r over h. Why this? Because the k is n pi over h, so I just plug the k in here. This is the k. I hope you can see this. This is the k. This is phi symmetry. What else do I have here? A sine. So the issue here is that the k here and the k here are the same. Right? So the k enters through the sine. This is the quantization, but it enters also in the Bessel function I0, that it's this one. This is our hero of the day. All this infinite amount of 4 types of Bessel function, only this guy came, and it looks something like that. 1 second. So let me write it down, n pi h, but now of z. Okay, I hope this is clear. Yes, what is the question?
We don't need to separate the solutions because this I diverge when we look at R infinity.
Yes, how exactly, you are right. However, we don't need to worry about this.
We have a boundary condition. We don't care about infinity.
But the potential that infinity is supposed to be 0.
Yeah, okay, so I'm talking about the V, sorry I didn't mention, I'm talking about the V inside.
Okay.
Yeah, this is super important. You have excellent question. V, R, phi, Z, inside. Yeah, this is very important actually. I forgot to mention this. So, what will happen outside is that when do you have generally quantization is when you have a finite system and then you quantize. But if you are outside, you have to integrate the solutions. We will have an example like this later on. But because then what will happen, these numbers, these quantum numbers will form a continuum because there's no boundary condition. Okay, we'll talk about that a bit later. So now we are done. We need to calculate these ANs. And how do we calculate it?
Projection.
By orthonormality of the basis. But the question is, what is the basis here? Is it the sign, or is it this I0? What is it? What is the trick to be used? I mentioned before orthogonality with respect to the j's, but you know that there is also normality with respect to the signs, like in Fourier series. So here is a slight trick. You need to understand which one of them to be used. And in this case, it's going to be the signs. So the horrible equation I gave you before with the zeros of Bessel functions, in this particular problem doesn't play any role. We'll have another problem that it will play a role, and this signs will give me this orthogonality that will eventually give me these ANs. So, maybe later I'll be sorry that I wiped this out, but still, let's do this. So, what is the boundary condition I didn't use? I used it on, I want to define boundary condition. It's not before Christ, it's boundary condition. And then this is R equal A, which was, again, this was this V here, so this was R equal A. And then I'm going to write this solution, I'm going to write it like this. I'm going to write sum V. This is a constant. What is this constant? It's a constant given on the boundary. We know what this V is. This is the input for the problem. This number is equal to the following, Bn, sum over n, Bn sine n pi z, h bar. And y, what is Bn?
An.
An?
IFS of n pi a over h.
Exactly. So n pi a, the radius, not r that we had here. R is anything between 0 and a here, divided by h. This is Bn, so I just plug it in here. And now this type of series, not a C, it's a sign. These are well known for you guys. This is just, you have a constant and you have the sign. So this is like a Fourier expansion. So what do I use? I use the orthogonality relation of the signs, not of the Bessel functions. This is what I said before. And this I think you know how to do. And if you don't know, I pray for your soul. So you multiply by sign and you integrate from z from 0 to h bar. Okay, so this is the usual trick. I'm not going to do that because it's in many courses behind. So I just mentioned, if you don't remember, it's okay, but remind yourself, easy to use orthogonality of Fourier coefficients. That's the way I see this. And with that I can get what is Bn, and then I can solve this problem completely. If we are here, then let's do this. So then we get the following. So in this, because this is a constant, not all the n's will contribute, because this V, this is something you should do in exams. This V is symmetric. I mean, it's so not all the n's of the odd functions will enter here.
Only even.
Yes. No, the n odd will enter, but these are related to the even functions here. So this just gives you the following: phi r, phi and z is equal to the following. For the pi comes from the orthogonality of the sign. It's an integration over this 2 pi thing, and then this is sum over the odd only. 1 over n. This 1 over n again comes from the orthogonality for these Bn's. I0 n pi r h I0 n pi a h. This one comes from this m sine n pi z over h. Same as before. Okay. This is the solution. Okay, now you can plot it and you can investigate this. But again, I just repeat the message. With this type of table, it's not so difficult to get to this type of solution. It doesn't mean that all cases are easy, because I exploited here the symmetry of the problem. There was a lot of symmetry in the problem still. We broke the symmetry a little bit, but not sufficiently. So let us look at another example, which breaks a little bit more the symmetry, and try and use the table again to solve the similar problem, which is still very different. Because up to now I didn't use the zeros of Bessel functions. They were not here, right? So let us give an example where we do have these zeros of Bessel functions. Where does it come from physically? What type of problems? So I want to define the following problem. I again have a cylinder. Here on top I have V. Here on bottom I have 0, and here I have 0 on the boundary. So I have a Coca-Cola can, and the top of it is V, and all the rest is 0 potential, and I'm solving the Laplace equation inside. Okay? So let us start. Again, let us start from the beginning. First of all, let us determine L, for example. We mentioned this already. In this problem, because I can rotate here from symmetry, from phi symmetry, let's call it, L is equal to 0. Thank goodness for that, because we don't have an infinite number of Bessel functions. We have only L equals 0. But this leaves us with 4 of them. We need to choose at least some of them. Okay, so the solution at r equals 0 is finite. That is, the potential is going to be finite, and is 0 on the boundary r equal a. I claim that this leaves only the Bessel functions. J0 remain. To make a claim that something remains, we need to say why the other guys are not remaining. So let us look at this a little bit. What about yi0? 0 again is from this first step. yi0 is not good. yi0, do you remember, or you already forgot how it goes?
I think because k
It goes up. There's no zeros of the I0. It's nice. You can make a rap song. No zeros of the I0. No zeros. So it does is not 0, is not equal 0 at r equal a. Out of the game. So I0 is bad.
יכול להיות אבל מצב שגם J, לא יכול להיות מצב כאילו שגם J0 וגם I0 משתתפים לו.
This is also true. That's a good point. Because either you're on this branch or you're on that branch for most of the problems I know. Yeah, but the way I see this is the following. It's easier to see that I0 is not part of it, that the J0 is. So it's easier to disqualify people than to say these are good people. So I want to do both. But you are right. I mean, so in particular, this means we are on now branch A, and kz squared is greater than 0. Remember, the previous example was this branch, and now we are on this branch. So we have here J0. Now we have sinh and cosh. no oscillations in the z direction, and this we also know how to treat. Yeah. No, this one, I'm looking, this I0, again, 0 is because L is equal 0, and then I'm looking at it, not at R equals 0, it's a bit confusing. I'm looking at R equal A, where you see the potential here on this boundary is 0. But this function is just going up. So it's not 0 on any point R. See what I mean? ציינתי פה כל כך הרבה ציורים. If I remember correctly, this was I0 of x. It started at 1 and it went up. This function doesn't cross 0 here in any place. And you want it to cross 0 because on this place, when R is equal A, you are 0 of the potential, of the real problem. This is the reason I disqualified not on R equals 0, which is in the middle. I disqualified for R equal A. The other two functions, which I'll discuss, even though we don't need them, is YL. They diverge at 0. So YL, Y0, and K0, they diverge at 0, and I disqualify them. Okay, so I hope this is clear, and if not, you can come. Is it clear or no? If not, come and ask me. Whoever is not clear, we can discuss it later, or just think about it a bit. These things demand some thought. It's not trivial. I don't think it's so trivial. And then what? So then I'm on this branch, right? What happens with this D and C? D? Capital D is 0. Why? Ah, yes. The guy said before I should define things. This is Z equal H. I define the Z equal to 0 here, and then sinch of 0 is 0, like the potential down here is 0. You see this? Then, okay, I'm happy with C, but D has to be 0. D is equal to 0 from, you see, boundary condition on the bottom of the can. So, to summarize this, I have a cinch, I have the J. What about these? Essentially nothing, because this one is 0, when L is equal to 0, and this is a constant. So we are done. We solved the problem. Not exactly, but we didn't do the orthonormality, but we can write it as an infinite series. So what is the solution? Let's write this out. Again, if you have questions, you should ask them more or less now, because essentially I'm done now with this solution, except for the normalizations and the prefactors. So what is VR? So the point is, from the table, phi and z, this is sum over some fn's. The f's come from the cosine, but it's not important. J0. Okay, here comes an issue. Zn 0 R over A. I'll soon explain this. Cinch Zn 0 Z over A. Okay, there are some steps I did here which I didn't explain everything, but or more or less, one of them is that this K and this K are the same. So you see this K and this K are the same here. This is the Zn0. And why is there a Zn0 here? It's very simple. If I plug here r equal a, where am I? R equal a, I'm on the boundary and I'm 0. So this is the solution. So this gives you boundary condition on r equal a is satisfied. This is the reason why I need this Zn inside here, in order to make this solution on the boundary 0. I hope you all see this. This is the idea of including this thing here. And once it's in here, because this is this k with L equals 0, then it must be also here. Okay? And of course, the cinch, again, this we already said, this 0, this is equal 0 at z equals 0. This also makes me happy. These are just checks. And this L, this is L equals 0. This is the symmetry of phi. And then we have this solution. Now, how do we get here Fn? Again, we have this maybe small dilemma, but not really, because the cinch is not a natural basis. It's not like the Fourier basis, right? It's not an oscillating function. So where do you get the Fn's? From orthogonality? From these Bessel functions and the equation I gave you before, right? I gave you an equation that gives you the orthogonality relation with a specific L. What will be the L? The L will be 0. And then I can multiply this by this J0. What will I get if you remember the equation?
J1.
J1, I'll get J1 because it's L plus 1. This will give you the Fn. So for homework, use orthogonality. Just mark in your notebooks of J0, get Fn. I'm not going to do this because this is a standard problem and I think you understand how to do it in principle, and if you want to practice a bit, you can do these integrals. It's very easy. Okay? Everything is Cativa. Cativa is good in Italian. I'm practicing my Italian. I'm going to sabbatical in Italian. In Italy. So I want to talk Italian. But I'm not speaking really well. So, okay. Yeah, maybe we should teach in Italian, not in English. So, let's have a break. And then after the break, we will discuss a little bit green functions and a little bit the image method. Let's have 10 minutes break. I really would like to finish the class end of chapter 3, as I mentioned, a little bit more. So yeah, let's be on time. 10 minutes break and then we'll continue. Okay, so now we want to change a bit, and we would like to solve actually the Poisson equation. And to do that, let us start with very general remarks. So what I'm going to use now is green functions, but I would say I'm just introducing it kind of physically, and the image method. These two methods are related one to the other, and I think you heard about both of them, but let's hear it again. So let us start from the most basic thing. The general idea about green function is the following. We want to solve different problems where you have only one source of charge, one charge. You say this is a bit crazy, because if you have one charge, the Coulomb law is holding. So what do I mean by that? You want to solve with one charge as a source, and then some boundary condition on the potential, and then it becomes non-trivial. If you know that solution for this type of problem, one charge and some boundary condition where the potential, let's say, is 0, then you can use superposition and find all kinds of other solutions. And this is used by this method called the green function. So let us start with a simple case where we actually don't have any boundary condition, just elementary high school physics. So we want to solve in principle the Poisson equation. And what is the Poisson equation? Let's put one charge only. It's really trivial. It's just in academy we like to make things a bit complicated. This is the Poisson law. That's the Coulomb law. That's all. But why do we do it a little bit more complicated? Because then we can generalize it. So you go up a hill, you pay a price, and then hopefully there is a reason for this. Okay. So bear in mind with me, there is a charge here, which I want to denote as capital Q. And what is this rho? This rho is delta x, delta y, delta z minus d. So these are delta functions, and this is the z direction, and this distance is d, and I put the charge there. So we'll see why I choose this d, but you can think about this d as 0 also. That's at this moment okay. And we all know what's the solution. The solution is Coulomb's law, which is simply 4 pi epsilon 0 square root x squared plus y squared plus z minus d squared. Okay, that was with no. In here, the boundary conditions are, if you want, are at infinity. The potential at infinity is 0, and this is the well-known solution. You also know how to take this solution and generate it to many point charges in a formal way by summing up many forces that will be superposition. But now let us do a slightly more complicated problem. And what we are going to do is we have a charge Q. So this is solved. This is just, we have a plane, an infinite plane, and we have a charge here Q. And this plane, I have here V equals 0. Now I want to solve the same problem. I want to calculate the potential. I have the Laplace equation. So I have a source. This source is going to be at D, at x equals 0, y equals 0, z equals d. And I have in addition this problem. Now this problem, you also know, I think. How do you solve this problem? Yeah, with the image method. So what is the trick here? Okay, let's start with the physics, because not all of you jumped at me. You should say, why am I teaching this if you know this already? And I want my money back. So let us remind ourselves, first of all, physically what's going on here. You have a charge here, Q, and here you have a potential which is 0. What is happening here physically? There will be some charges here which will compensate for this charge in such a way that the potential in this plane is going to be 0. How much charge will be here? Minus Q, you kind of intuitively understand. So there will be a charge density here that will build up and counter this potential in such a way that there is no potential. Now, if someone will tell me, this is the charge here, give me the charge, not the potential, then in principle I could go back to this problem for each point charge, and then I need to integrate over all the charges, and I'll find the solution. But the problem is that no one is giving me a priori this charge distribution. We will calculate it. What is given to us is not the charges like in here, but just the potential on this boundary condition, and that's why we need a different method to solve it. And one method is the image method. What is the image method? What do you do?
More charge.
You put another charge here, the minus. This will get you V equals 0. And this solves the equation, and because of uniqueness of solution, this is the solution. This is very nice, but maybe when you saw it for the first time, you asked, how did the guy or lady or whoever, how did they guess this idea to put here a minus charge? And I'll remind you soon that, how did they do it? They were very clever people? Or maybe they worked hard and they got it. What do you think? I don't know. I have no idea how the first guy got it. So what will we do here? We will start and solve this problem as if we don't know that we need to put here a charge minus q, and we will find it in the hard way. Why do I do things in the hard way? Because in general, when you encounter a real problem, not this simple problem, it will be the hard way. What is the harder problem? Let's say this surface is a bit wavy or something like that. Then what do you need to do? You need to expand in an eigenfunction expansion like we did in the previous class. And I'm just telling you if this is flat, everything is easy and I can solve it in a different way. So let us solve this problem with this marvelous table. It's easy, not difficult, but there are some integrals that are difficult, but it's not so complicated. So first of all, if I want to use this method, what do I need to do? I need to first of all define the coordinate system. And of course, it's on the blackboard, right? So which coordinate system I'm going to use? The cylindrical coordinate system. Why cylindrical? I have a plane here, and then I have one charge on top, right? This will be the z-axis. What about the phi-axis? Symmetric. What is L? 0. Ah, okay, that's already good. We got rid of these awful functions here. Okay, so we are going to use the cylindrical coordinate system. So here is the charge. This is times d, and I'm going to write here phi. So we have here what I called before phi symmetry. That means L equals 0. Maybe you can already see what will be the difference. There are many differences from this problem to the previous problems, but what? Maybe someone wants to mention one of them or a few of them. First of all, what is happening? We are going here till infinity when we go up. There's no boundary condition in this direction. This is related to, this guy, he left. But he asked me, you move. Okay, so what does this imply? Maybe you see a few steps forward in this game of chess. Yeah, the K will not be quantized because it's an open system. Now let us look at the table, as usual. Let us look at it. So, okay, here L equals 0, all this is a constant, right? What is happening here? Is it going to be a sine and a cosine? When you go up, very far away to the moon, the potential has to decay at plus infinity. It's not oscillating there. So, potential, so this is 1 point. Potential is decaying. But let us be more specific. When the z coordinate is up here, very far away, going to infinity. What does this mean? First of all, let's cancel no sine, cosine solutions, right? But if it's decaying, what is it? Of course, it's some linear combination of sinh and cos. But what is it more specifically? E to the minus kz, the solution in z direction. It's decaying, it's not exploding. E to the minus kz. K is going to be a continuous variable now. The fact that I'm in this branch means that I'm in A. I'm on this line, kz greater than 0. We mentioned that L is equal to 0, and as before, I'm not going to show this, the only thing that is remaining here is the J0 of Kr. So the solution is going to be composed of J0 and this exponential. There's no phi because of symmetry. take these two functions, multiply them, sum, but not sum, integrate, again, because k is going to be continuous because there's no boundary condition, and the solution is done. Okay, so let us write it down. I hope it was more or less clear, or at least it was clear that this table is useful, and the solution is V. This is the solution in Z greater than 0, first of all. So I'm looking up here. You can ask me. Okay, she doesn't want to ask me. I'm looking at the solution up here. What is the solution down here?
זה לא משנה.
Every time I ask you a question, the answer is 0. Trivial. It's 0. Why is it 0 down here?
Zero boundary conditions.
Yes, and what else? That's true.
No,
It's like a Faraday.
0 boundary condition, but also on top there is 0 boundary condition.
It satisfies.
yeah, but there is no.
There is no
He's a good lawyer. It satisfies Laplace equation. The second derivative of V is, if you take 0, that's a solution, and it satisfies the boundary condition, and if it satisfies the equation, again, because there's no charge here, then it satisfies the boundary condition, we are all happy, and we are equal. So now I'm going to talk about Z equals 0.
Didn't we add a charge, like under 0?
No. I want to derive that.
Ah, okay.
I want to derive that, so you used to like physics, and after this course you will hate the physics. I'm making things complicated in order to simplify them.
Yeah, it was.
Okay, so before doing that, let me be a little bit more precise. Okay, so let me be a bit more precise. When we saw, okay, so first of all, when Z less than 0, V is 0 everywhere, as I mentioned just now. Okay, good. Now, what I want to do is the following trick. I'm going to write Vx, y, z at the beginning. Later I'll go into the other coordinate system. And we do have a charge. This is, she reminded me, we do have a charge. Where is the charge hiding here? Okay, so what is the solution I claim? I'm going to write it in the following way. I'm going to write it as Q 4 pi epsilon 0 square root x squared plus y squared plus z minus d squared. What is this? What is this potential? This is the potential because of this charge here. This potential by itself does not satisfy the boundary condition on V equals 0. But what I'm going to do, I'm going to add here some potential V1. I add here some potential, and now the problem will be to find V1. Why this is the solution, by the way, the second derivative, the Laplacian of that part, what will it give you?
Delta function.
A delta function. This is very important in this business. The Laplacian of this solution, this was already in the class, will give you a delta function where? On D, and that is the charge density on D from a point charge. So now it is easy, I think. I just plug this in here. And what is the equation for V1?
Laplace equation.
It's Laplace equation. This is what she said. Maybe she didn't intend, but now it's clear. Okay, good. So I'm going to solve this equation. All what I said here was for V1, not for V2. And what is the boundary condition for V1? It's not V equals 0, right? The boundary condition is for V, not for V1. So the boundary condition for V1 is
minus Q.
Minus of the thing here. So the boundary condition for, I'll soon give you the boundary condition, but the boundary condition for just now for V is not the same, it's trivial statement, as V1. And soon we need to say what it is, the boundary condition for V1. But there is some boundary condition. But in this table, there's no boundary condition at the beginning. Remember, what does the boundary condition eventually give you? The prefactors by these orthogonality relations, right? So the boundary conditions are super important. They will determine everything. But the first stage of the solution is selecting the proper solution. And this is what I said before. Again, we said there is no L. This is a constant. This is an exponentially decaying function. And this is only L equals 0. And this will be for V1. And then I solve the problem more or less, except for calculating the coefficients. Everyone is with me? If not, tough luck. No, seriously. Is there other questions? Are there no questions? Yes?
Why the solution for Z greater than 0? Why is the Z solution E minus KZ?
It's for V1 only.
What do you mean?
Remember, okay, just I'll try and answer you and then you tell me if you understood or not. The previous class, what we did in previous class, we had just the Laplace equation. We did not have this one here. So what I'm saying here, this solution, when I apply the Laplacian, I didn't write it, but maybe, I think it's pretty obvious. If I apply it on this part, it satisfies this part when this is a delta function. And for V1, you get this usual Laplace equation. Is this clear?
Yes, that's what I asked.
Okay, so ask again. I mean,
for when you solve for Z greater than 1, you found the solution.
it's greater than.
Greater than 0.
Yes.
You found the solution E minus KZ.
Yes.
It does not satisfy the boundary condition.
No, it does not. Okay, you are right and you are wrong. It does not satisfy the boundary condition of what? You are saying V is equal 0, right? But this is V1. This is not V. That's the point. So you need to satisfy. Soon we'll say, but it was mentioned already. We need the boundary condition of V1, not of V. Otherwise, you would be absolutely correct. But if I use V, I cannot use this method. This table is not good. This was what I was trying to say at the beginning. This method is not good for V. Why? Because you have the charge. So you need to first get rid of the charge, define a Laplace problem, which is what I did here for V1. You get a boundary condition that you need to determine. It's not so difficult. We will soon do that. But V1 is a Laplace equation. Then you can apply this table. Okay? Thanks for asking. So, okay, so now we are at V1, and I mentioned already I had all these arguments, and we can solve for V1. And it's pretty... it's the following thing. And again, if you don't believe me, then you can just plug in and see that this is an equation. This is a solution. So again, using the table, L is equal to 0. I get the following solution. V1 is an integral. This is what I mentioned before, that you don't have quantization because you go upstairs and there's no upper boundary, so there's no quantization. And then you have some function of A of k. This we need to determine from the boundary condition. And then, as I mentioned before, I have J0 k of r e to the minus kz. Right. So I hope you all see how I came for this. I took this part, this decaying part, in order for it not to diverge at infinity. It does not diverge at infinity. That's why you cannot have a plus. You have this line. This is the Bessel function, and then you're on this line, and then this y was deleted. So this is the solution. And now comes what is the boundary condition for V1. So V1 on the boundary, V1, R, phi, and Z equals 0. What is it? It's exactly, let me write it down. It's exactly this, minus, the minus is super important, Q, 4 pi epsilon 0, R squared plus D squared half. Remember the R, you have here a point and you're going out in the plane, that's the distance R. Z is equal to 0 in this equation, so R is x squared plus y squared. Why is this the boundary condition? You see this?
כי זה צריך להיות 0 ועוד, אם אתה מציב כאילו...
Yes, it's very simple, because V, what is it? It's cube, let's write it at Z equals 0. I'll write it here. It's 4 pi epsilon 0 R squared plus D squared. R squared is x squared plus y squared. Minus Q, this is the V1, 4 pi epsilon 0, R squared plus D squared, this is equal to 0. So this is the boundary condition. This is a deeper answer to your question. It's not 0, it's this. It's negative. At R going to infinity, it's 0, but generally speaking, it's not 0. So you have here, this V1 has a property that is decaying when you go out. What does this boundary condition give you? This boundary condition gives you A, right? As usual. Boundary condition gives AK. But how exactly do we do this? There's no zeros of Bessel function in the solution. There's no signs to help me. What do you need to do? You need a toolbox with many tools. Or you need to ask ChatGPT or whatever. There's another trick. And this is a message here. There are many, many tricks here. It's not a simple thing. You look at a different type of orthogonality, type of relation that does not involve the Bessel functions, does not involve zeros of Bessel functions. And if you know this trick, you can succeed. And if you don't know it, then, at least for me, you are in trouble. So I need to teach you another trick. What is the trick? What do I actually want? I want to embed this. I want to plug in here V1, and I want to get out of this some delta function in order to get this AK. So I go look in a book of Bessel functions, and there are millions of equations. It's not, believe me, on Bessel functions, you have books on Bessel functions. It's not easy to find these kind of equations, but one of the equations you find after hard work is this equation, J0. J0 is good because L is equal to 0, so we are in the correct game. KR J0 QR RDR is equal to delta Q minus K. Of course, you cannot remember this, divided by Q. And this was a question in the break. This actually holds for any L, also fractional L, but not for L less than minus half. So, and this is a, yeah, okay, so, because I guess at R equals 0, it doesn't converge or something like that. So this is a nice thing. This is the delta function here. So what does it mean? I need to plug in here this V1, and then I need to integrate it by this J0K Q. Then I'll get a delta function, and then I can find AK. Do you see it more or less? Is it clear more or less what to do? Not the details. Is it clear? Okay, so let's do it. I guess all of you are already tired. Then So let us write it. Where is this? Okay, this one and this one use multiply by some J0 QR, integrate over R, actually I think I need to multiply it also by an R because of this one. If I do that, I'll get a delta function after integrating over R, and what will remain? Integration over K.
With the delta function.
With the delta function, even I can do that. And then I'll get the AK. So again, I leave this for homework, but what you get, or what I got, is AK divided by K is minus Q. That's not so surprising, it comes from this here. 4 pi epsilon 0. Integral from 0 to infinity dr r j 0, again this is because of L equals 0, r squared plus d squared. Why do we have r squared plus d squared? This comes from Coulomb's law when z is equal to 0, and this is the decay like you have here. This is my AK. Okay. Then I scratch my head. Then what do? I go to ChatGPT and ask him to solve this this thing. This integral is luckily enough minus KD divided by K. Now what do I need to do? I take this and I plug it in here. I plug it in here, and then I have another integral now over K. I need to pray that I can solve this second integral. One second, but unless I made a mistake, then tell me.
I think it's a mistake because you multiply with R G null, and R I think comes from the Jacobian. So you multiply with R.
But I just deleted it. You mean this R?
You say you multiply R J null, and R comes from the Jacobian.
Okay, so you say it's without the R?
I think.
Yeah, but I just deleted this. But wait, let me see. We can check this easily, but what I was trying to say is that in the orthogonality relation, I didn't have an R, so I added one R, but you say it was already there.
I think when we switch to integrate the R and not X and Y.
No, this has nothing to do with X and Y. This is related to the, okay, I have this relation, so let us write it. You have minus Q, 4 pi epsilon 0, R squared plus D squared over half, right? This is equal to this integral dk ak j0k of R, and it's on z equals 0, so this is 1. dk, right? Oh, I have already dk. Agree?
Okay.
Now, what I said is if I multiply this by J0Q of R, and I think you need also an R here, then I need to also integrate here J0Q of R and R, and now I integrate over R.
Now when we integrate over R, we don't need to add the R.
No, I just integrate over R.
Okay.
Because what am I doing here? You see this function and this function, the formula that I had here before, this gave you the delta function. Because of some mathematics, it's nothing to do with the Jacobian.
Okay.
And this is a delta function. After I do the integration of r, and then I can do the integration of a k. And then I'll be left here with only with aq divided by q. There will be a q, then that's all.
Thank you.
Okay, so okay, I have now ak is simply an exponential function decaying with d, and that's it. We have ak, and then we are ready to wrap it up because now I can put this ak in here. So I can plug it in, and then I get the solution. So V1, again, this is the part of the potential, not including the Coulomb part, the simple part, which is due to the charge. So to get V, I just need to add something. This is equal to the following integral. Okay, you have the minus q 4 pi epsilon 0. Integral from 0 to infinity dk, this is this dk, j0 kr, and here I have akz minus kd. This is my potential. So kz just implies decay when z is big. This minus kd came from this ak. And what is this object? One of our heroes is Laplace. This is related to this. So this is a name. It's not very useful. This is the Laplace transform of this function j0. Laplace transform with respect to k, because here I have z plus d. Now what do? We go to the Kotel, we put a note, and we ask God to help us solve this integral. And what do you get?
Point charge.
Point charge, exactly. So this so happens, this is going to be a point charge, this V1. I'm not showing it, I'm not proving this. This is just mathematics for me. VRZ. It's not just a point charge, but you are absolutely correct. It is a point charge with a minus sign. And where is it? Well, I told you already, because I know you cannot live without in the suspense for so long. Notice what is important here are two things, well, maybe more. First of all, it's Coulomb law, of course. But the important thing here is the plus here and the minus here. So it's a negative charge, and where is it located? Underneath the plane. So this is a Coulomb force, a Coulomb potential. Of charge minus q located at z equal minus d. Now we stop and we think why this is correct. This is something most of you know, but I'll remind you anyway. Why is this correct? And why, in some sense, we can guess it? Can we really guess it? We can cheat the students and say it's trivial, but it's not. So what is happening, and this is something you know, and it is the following. I have, let us start and solve the problem in 2 seconds now. I have a charge here, and I say effectively I have a charge minus q here. This height is d, this height is minus d. What is the potential due to these two charges on this boundary? V is equal to 0. This is not V1, this is the total V. Why? Because every point here You have a minus q and some potential. It will balance here. The potential is 0. Okay, so the boundary condition is solved. What about the Laplace equation? Sorry, the Poisson equation. Is it solved? Here there's a small point. Where do we solve the Poisson equation? Above. The Poisson equation above will, this charge, when you do the differentiation above, what will it give you? Nothing.
0.
Because it's a delta function, it gives you a delta function here. This one, when you take the Laplacian, will give you a delta function here where the real charge here is. So this is the solution, at least from a physical point of view. This is the image method, where you have a plus q and a minus q. And if it's not so clear, then you need to think about it. There is one small thing to remember. It's not that this image charge gives you the potential correctly here. Here the potential really is 0. It's only the solution up here that it gives you the correct solution, okay? So again, the real potential down here is 0. Up here it's due to these two charges. This is what this solution tells you, because this is V1 for coming from here, and V in the first part, this part coming from the charge, gives you the boundary condition, it solves the Laplace equation, and this is the image method. Okay, so of course, when you are at high school, I don't know where do you learn image method, I don't remember, if you want to remember. Let's say high school or first year, they teach you this method, right? But what do? They say, I think that's what they do, maybe I'm wrong.
I don't think they teach that.
They don't teach that.
Oh,
This is the deterioration in your generation is so bad. No, they don't teach it.
I don't know.
But some of it.
סמסטר מקוצר, אז לא הספקתי.
Because of the war and because of COVID and all kinds of
3
things.
years ago they teach that.
You teach that or you taught that?
No.
Where?
They taught that. Schneer taught that 3 years ago.
Okay, yeah. Also, I taught it 3 years ago. So what? The question is, did you learn it?
Yes.
Which there, when you
Yes.
come here to the course again?
No, in
Electrostatics 1, right.
In physics.
Good. Someone listened to Schneer, that's good. In electrostatics 1.
No,
It's not electrostatic, it's
electromagnetic. כן, בחשמל המגנטיות.
Yeah, in the first year.
Yeah.
Okay,
Let's
so
talk about it.
let's say the following, that this was taught somewhere in the past by Nadav Schneer, but I don't think maybe I'm wrong, did he teach you all this
No.
derivation? So there are two different things. So on the one hand, this is something that bothers you, or bothers me. In physics, at least in my case, because I'm not so clever, usually what I do is I work hard, and then I get something simple. And after you get something simple, then you can justify the simplicity by some simple arguments if you are lucky. This is the usual way that physics goes on. You solve things, and you pay some price, you solve these integrals, it's not so nice. Then you get a nice result, and then you think why it's trivial. Then you tell the students, it's a trivial problem, here, take it. But it's not like that, it's never trivial. This was my message, and the second message was, what will happen if this surface is not flat? Then I cannot solve it exactly, honestly. But you understand that with some numerics, I can expand the solution with a linear combination of Bessel functions and maybe find the solution, and it will possibly give you the same. And what is the third advantage? Now that I solved this with a charge, let's do something slightly new. I hope it's new. What will happen if I have here a charge density? So I want to ask you, what will happen when I have here a charge density on top? Underneath there's no charge density and the potential is 0 here. How do you solve
You
that?
will have an equal and opposite charge density down below.
Exactly. That's the physics of it. And we will use kind of this type of solution to solve it. So the claim now is that with this one charge, this is the green function method for physicists, we first solve for one charge on top. Then we use superposition, and we can have, in principle, up here any charge distribution. I still assume now that the potential is flat. This is just superposition. Okay, so we will do also that. So But before doing that, let us have some remarks. How do I calculate sigma n, the density here in the plane? Okay, what is the sigma? The charge density on the way on the plane, which is the real physics. There's no charge here, but there are charges here on the plane. There is real charges. You can come with a tip and measure them. If you measure here, you'll find nothing. What is this? How this is given? Sigma is again charge per unit area. This is the usual definition, and this is given by dv over dn. This n is the vector in this direction, also that is normal to the plane, and I know the potential slightly above here. I can take the derivatives here. I leave it as an exercise, and this is the potential is 0, but its derivative is not 0. That's the point. This is minus qd 2 pi x squared plus y squared plus d squared to the power half. So what does it mean? It means that the density is first of all negative. This is which is not surprising because you are balancing a plus charge up here, and they are kind of more density in the middle, which is obvious because you need to compensate, and you see when r, x and y become big, they decay like this. Now, if I take this sigma and I integrate over all space, and here I do need to use the Jacobian that was mentioned before. It's r dr now, but he was mentioning before, the usual thing. Integrate.
Maybe you can integrate
Over, I don't care how you integrate. Space xy plane, you get total charge minus q. So this is what we mentioned. This is called the induced charge. It's located kind of here, and its total is minus q. You can ask, where is the charge coming? It's coming from a battery, or you can also think about this. This plane, let's say, is neutral, and some of the charge of it went to plus or minus infinity, and you have some charge here to compensate on this charge above. Okay, so now this image method is not limited to this plane. You have an image method that will be at homework for other geometries, but this image method is limited. It's not that you can solve any problem with this image method. Again, that's the reason why I bothered with all these Bessel functions, which are more general in some sense. So image method you can use for, let's say, a sphere, and here the potential is 0 and q outside. And you can find where will be the image somewhere inside the ball. It is more complicated. It's given in Griffiths, and it's important because, again, what I'm trying to say, once I have this solution, then I can have a superposition of many of these q's. Any charge outside here will give you, by integration of all the q's, you will find the solution in the presence of some symmetric thing. This is homework and reading in Griffiths. I'm not solving this one here. Okay, so now let us see how you use this for more general problems. So, what is exactly a green function? So, the green method. So let us start with free boundary condition, which is a trivial problem that will allow, this is just, there's no zero potential on the surface nowhere. So this is a trivial problem. Let us define some coordinate system, x, y, z, and then I have r prime. This is one charge. So again, green methods, what is the strategy is always solve a problem with one unit charge, and then from that one you can go to more complicated problems by integration later on. That's the general idea, one of the general ideas. Then I have some point in space, which is going to be on R, X, Y, Z. This is just a point in place where I want to know this potential of this Q, and it's simple because it's free boundary condition, so we know what's the potential here. It's just the Coulomb's law, nothing more. And here I just want to define, this is this distance R star. It's a vector. So, okay, so what is V, X, Y, Z? This is undergraduate kindergarten. So this is 4 pi epsilon 0 and Q over R star. This is just Coulomb's law. What is the density in this problem? It's a delta function, which I'll write on R prime, because Q is on R prime. This is a multiplication of 3 delta functions, and Q is the charge. Let us write down the most equation. I mean, the mathematical tool that is behind all this is going to be this one, R, which is known for you. This is not new. The Laplacian of this one is,
The function, I think.
here I have a delta function. This essentially is what people will call the green function. In this problem, not in general, for free boundary conditions. So just what I'm doing here, I'm just giving it names in a trivial scenario just to prepare you to something a bit deeper. And what is the idea? Which is essentially the Coulomb law. You see, it's 1 over R star. So the general idea that was, it's kind of, we know this, is that the general solution we can write as integral over the whole volume, the whole space, rho of R prime, G1 R minus R prime. There is an epsilon 0 here. And dV. So what is this? This is very simple. You see, this is the Coulomb's law. 1 over 4 pi epsilon 0, 1 over R minus R, and I have a charge density and I integrate. So what I'm trying to tell you here, something trivial? Yes. There is a function G that if you give me the density of charges, I integrate, I get the potential. And here it's nothing but the superposition. So what is Green's question? Now I can pose the question. We want to find this function G not for free boundary conditions, but for other types of boundary conditions. Some transformation that will take you from a charge density that in general you don't know, but the guy 1 will give you 1 charge density. Another guy will give you a different charge density for problem 1 and for problem 2. But you will have some function G for Green, and then you need to do this horrible integral. I'm not saying it's very hard sometimes to do the integral, or you do it numerically. you have it. And then our goal, or the goal of green, is to find this G for different boundary conditions on the potential for, let's say, when we do not have free boundary conditions, for example, in this problem. And for this problem, it's very easy with the image method to do that. But more generally, this is the meaning of the green function. So again, you solve a problem for one charge, but with maybe complicated boundary condition, and then you can generalize it to very general charge distribution and solve the Poisson equation. What is the idea here? The idea is very simple. I solve one problem, get G, and that's a solution to all the problems up to an integral. Of course, that's a bit cheating. But what this green saying is, let's find these guys. Later on, you tell me what is your charge density. You do the integrals. I just want to find this. Later, you solve the problem. You understand this strategy? I mean, that's his idea. That is why this function G is so important, and we call it green. G is for green. But of course, the question is, how do we find this for different boundary conditions? That is not easy in general. That is very non-trivial, but at least for this problem, it is not so difficult. And it's exactly the physics that was mentioned before. This guy mentioned it. It's not different. So green function in this case is very simple, in my opinion. So what is the claim in this problem when you think about it with the flat potential 0 here? One last thing. When I say charge, I mean the charge is up here only. In principle, you can separate it to charge up here and charge down here, but let us think only charge up here. So what is the green function in this problem? I'll write it down and then I'll say it. V equals 0 for z equals 0. Green function G of R and R prime. So it depends on two coordinates, like here. Again, R is where are you in space. R prime is where is your kind of charge in this one, right? And this is given by this simple idea. X prime minus x squared plus y minus y prime squared plus z minus z prime squared minus x prime minus x squared plus y prime squared plus z. And here is the one of the points. Here there is a plus z prime over square, and I need to take the square root here and the square root here. So what is this? What is this thing? What do you have here? This is mass, but what is it? It's very simple. It's, forget about the charge, the Q is equal 1. This is a source term at z equal plus z on the top. This is a source term on the bottom. And you have the minus sign. So what is the physics here, at least, without, I'll soon interpret this, what is exactly this means. This means I have one charge on top, one charge on bottom. And these are the image method, right? This is the same thing that we had before, just I write it now in an equation. But what does this give you explicitly? Explicitly, my claim, this is still claims, x, y, z is equal to integral over the volume of all space, but soon we'll discuss this, of this R prime. So I have some charge density, above the, let's say above the plane, times G R prime over epsilon 0 dr d volume prime. And this is the solution of the Laplace equation. What Laplace equation? With some charge density rho, whatever it is. So we have here
Poisson equation, no?
Poisson equation, sorry. So here I have P of R. Here I have 0 potential. For the sake of discussion, let's put the charge down here, 0. So what is going on here? This is what you said before, but written in math. Each charge density, think about this as kind of combination of delta functions. You have a negative charge, and a corresponding positive charge above and below the plane. This is what this equation tells you. I can have a complicated one again. I cannot always solve this, but this is going to give you the solution. Now the question is, why is this the solution? I try to kind of explain it more from a physical point of view, but now let us see why this is an equation. Why is this a solution from a more mathematical point of view? So what will happen when I apply here the Laplacian? That's what you need to think about. I apply here the Laplacian. On what coordinates does the Laplacian work? On x, y, and z. Where does it go? It works on this r, not on r prime. This is the integration, right? So I need to look at the Laplacian of the g. Of course you can do all the math, but I don't suggest that. What is the Laplacian of the g?
Two delta functions.
This is this equation that I had here before. It's two delta functions. One of them is in plus z, and one of them is in minus d. These are the two charge, image charge. So you see, everything I teach is like what Nadav taught 3 years ago. It's exactly the same. No, not really. But do you see this? So the Laplacian of this guy gives you a delta function, both on top and on bottom. But the guy on bottom, is it important?
No.
No.
Why is it not important? Because I integrate over rho of r, and there's no, this density is 0 down here. So when I take the Laplacian, I get out of here a delta function. When I get the delta function, even I can integrate the delta function. What do I get? I get rho of r. Because this will give you a delta function on r minus r prime. I do the delta function integration, this will be rho of r. And that is what? That's the Poisson equation. So, okay, these steps might be not immediately clear, but this is what is happening. So let us just write it down. So, okay. So from this, so just a reminder, first of all, this is the problem. Some charge density up here, 0 charge density here, V is 0. This is the definition of the problem. B, potential x, y, z is equal 0 for z less than 0. This is what we said before. It solves the Laplace equation. We don't need to solve it again. The difficult part is to find the potential up here. We operate with the Laplacian. And then this is what I said before, dg r prime. This is minus delta x minus x prime, delta y minus y prime, delta z minus z prime, These are the two delta functions that I was mentioning. Why? Because this I'm operating on this part and I'm using this one. And here I have minus delta x minus x prime, delta y minus y prime, delta z. Now here I have the minus, so here I have a plus z prime. Okay, so we apply delta squared on v x, y, z, right? And we use this equation here. I get out these two delta functions as I mentioned before. One of them is not relevant. Ah.
You do not integrate on that part.
One of the integral of the delta functions not relevant. Because of integration over the density that is in here. So there's only one delta function. Then the last point, point A, integrate over delta function. You get rho of r, and there's an epsilon 0, so Laplacian of v with is equal rho divided by epsilon 0. And what is the last thing I have to show? Just to check the boundary condition is satisfied. And this is easy to see from here, because if I plug here x equals 0, then the square here will be the same, and then you'll get 0, and that will just give you, again, here you need to plug in x equals 0, y equals 0, z equals 0. This will give you 0 here, and then vx, y, z is going to be 0 on the boundary. Sorry, that is for z equals 0 here. When z is equal to 0, yeah, this guy and this guy are the same. Vx, y, z equals 0 is equal to 0. It's again easy to check. So this is the solution. So, but physically it's very simple. It's exactly what he said. You have each charge as a negative charge below, then you integrate. This is this green function solution. I just want to repeat. You can do the same thing, let's say, for a sphere and the charge is outside the sphere. You can do it in more complicated things, like an ellipsoid. But then usually you will need to find the green function by numerical methods. So if you want an analytical expression for the green function, a simple thing, usually you use the image method. But the green function is more than the image method, because if you don't know how to find it by some symmetry, by some nice tricks, you simply solve it semi-numerically and you get the green function, then you plug it in and you solve these type of problems. But that's way harder. I mean, and the intuition goes down the drain in some sense. Okay, so now I guess we should stop because I guess it's a bit too much for everyone. So what I'm asking you to read, it's important for next class. I want you to read in Griffith's chapter 3. This is something I didn't manage to do today. The multiple expansion and the meaning of a dipole, it's part of chapter 3. And then chapter 4 is what we are going to do. is using the dipole. So I'm going to assume you all know what's a dipole and what is the multiple expansion of a dipole. So this is, let's put it this way, this is the A for the next lesson, which is to use these dipoles and find the electric fields when you have many dipoles. Okay, so I guess I wish you nice holidays. There's no lesson next week, right? Okay, please check.
אני